Okay, thank you. I know this is the last talk. I'm the only one between you getting home or to the social event, so I'll try to keep it short and very practical. Thanks for the invitation. It was really interesting to hear the talks. I was only able to catch half of the talks, but they were quite interesting. But maybe I'll provide a little bit of different perspective coming from the RDF Sparkle world. So I'm Evren Sirin. I'm the CTO and co-founder of Stardog. And before talking about what we did with LDBC, our experience, I'd like to give a very quick overview of what Stardog does. So it's you can think of it as a graph database in its core based on the RDF data model representation. We have the support the RDF star extension. We call it edge properties. I'll talk about then the connection to LDBC. One kind of differentiating feature we have is you can load all the data into Stardog more like a standard graph database, but we also have the ability to virtualize external data sources like SQL or NoSQL databases as graphs. That allows you to run like a Sparkle graph query that we will automatically translate to SQL or like MongoDB's query language and so on. You can also run SQL queries against Stardog as well. At that point, we take input SQL queries and translate it to Sparkle and potentially to the external data sources as well. So if you are storing data in Stardog, it's we are using RuxDB to store the data. And for the virtualization part, we implemented our virtualization engine using Calcite. We implemented the MySQL protocol, so you can treat Stardog as a MySQL database to connect from BI tools and so on. So that's kind of the very quick summary. And let's see. We have been kind of following LDBC from a distance. In the past, we have looked at, I think it was called semantic publishing benchmark, for example. We were obviously aware of the social network benchmark, but we have never really gone and digged into the details or tried to run the benchmarks. Of course, benchmarking is very important for us. We have 100 different benchmarks we run every night. Lots of standard benchmarks like Berlin Sparkle benchmark, SP2B, things like that, but also lots of benchmarks we have created from like real world use cases from our customers and users. But since last year, we started looking at the social network benchmark in a little bit more detail and started running it more regularly. But our interest has been mostly due to time constraints. We have focused on a subset, so we are only looking at running the read-only workloads. So backload the data at once and then run the interactive complex query mix. We are only focused on the case where all the data is materialized in Stardog and all the queries are being executed using Sparkle. And we have taken the Sparkle queries that was in the LDBC benchmark that have been kind of deprecated right now. And we have not made any changes to the queries themselves. I'll talk a little bit about that. Obviously, making tweaks to the queries is like one way for improving, but we've tried to not change anything. I mean, in the future, we are planning to maybe look at how the SQL queries over Stardog would perform as well. We do that for like Berlin Sparkle benchmark comes both with Sparkle and SQL queries. So we do benchmarking using those different interfaces against Stardog. So that would be interesting for us to look for LDBC as well. And since we started looking at, we've found like some simple and not so simple improvements our query engine. I mean, compared to, so the version 7.5 of Stardog, it was like early last year, I think February, March. compared to today, the performance have improved like more than 3 times in the current development version. But there are some challenges, and I'd like to talk about the challenges we have faced related to the benchmark, the technology, and query optimizations as well. We don't have too much time, so I'll just kind of briefly mention each of these. I don't want to actually talk about tooling challenges too much because it's mostly us, as I said, due to like not having enough bandwidth. For example, we didn't really take the existing LDBC drivers. Like we had some problems running down. Yesterday, there was a mention of the second version of the interactive complex data generator will be much faster. I'm very happy to hear that. Like we've seen like slower data generation and so on. But mostly since we didn't spend too much time on figuring out the tools, we have simply like generated queries and run them using our own benchmarking tools so far. So talking about challenges, the first one is the very obvious one, and it's like one of the things that's always mentioned as the main differentiation between RDF and labeled property graph systems, attributes attached to edges. And this is a very key part of the social networking benchmark. Most specifically, there's a relationship between person instances, the nodes relationship, and there's a date time associated with that nodes relationship. And the standard RDF representation, you need to introduce an additional node to represent that kind of edge property, the reification approach. So what that results in is whenever you want to find the 2 people that know each other, you need to go through another node, one more hop in the graph. As a result, this means like additional joins when you are answering queries, and makes the introduces an overhead. And but today there's the RDF star Sparkle star extension that has been proposed. It's not a standard right now, but a lot of systems, including Stardog, supports a version of RDF star. And RDF star, actually, it's kind of a superset of edge attributes on labeled property graphs, because you can use edges as like objects of relations as well. But it's also allows you to represent this kind of edge attributes in a straightforward way. This makes the queries much simpler. And in the social networking benchmark, since this nodes relationship is used pretty much in all the queries, that makes quite a difference. We have created a version of LDBC that uses the RDF star representation and updated queries to use the Sparkle star syntax. And when we compare the vanilla RDF versus RDF star implementation, we see 20 to 30% improvement. We haven't updated the data generator. We've just transformed the data on the fly. But at some point, we would like to contribute these kind of changes back to the LDBC repo. Okay, so continuing, another challenge in Sparkle is like all patterns in Sparkle are directional. So when you are trying to find 2 people who know each other in either direction, you need to use union property paths, inverse paths, just like in the Kevin Bacon example we were seeing. And also property paths in Sparkle have regular expressions, but they don't have any kind of limits. One very key feature of the SMB queries is to find people and their friends that are at most 2 hops away. So that means you need to use these more complicated union operations in Sparkle. That's both harder to read and not necessarily very efficient. So as was the topic in the previous talk, there's no short spat feature in Sparkle. Property paths only returns the nodes. But as was pointed out, several RDF systems provides a short spat extension, including Stardog. So this is our like Sparkle-based syntax for finding short spats, where you can have basically a graph pattern to specify the start and end nodes, and then a pattern for representing how the nodes are related to each other. And as a result, this query will return the paths between the start and end nodes. All short spat between the nodes will be returned. There's even an option to return all paths in general. So this query we are looking at, it's the query 13 in the interactive complex benchmark. But we also recently implemented the ability to embed these kind of path queries into select queries. So one of the things we'd like to try next is use this kind of short spat queries within the rest of the social network queries. Okay, so I'll talk very briefly about query planning challenges in Stardog related to LDBC, but just for the, I need to talk about how query planning in Stardog works. And there have been like some discussions about using relational systems, navigations as joins, and so on. And Stardog is a graph-based system from ground up, but our technology is actually based on relational literature more than anything. If you are familiar with Thomas Newman's work on RDF3X, that was one of our original starting points. And our query engine uses like a standard volcano model. The triple patterns in the query are translated to index scans. The basic graph patterns, or basically multiple triple patterns, are translated into joins over scans, and then you have various different joins algorithms to combine them. Obviously, there are other algebraic expressions like the unions, filters, and so on. They get represented in this query plans. And the information, which is in this case Sparkle solutions, each index scan generates some solutions. They flow bottom up from the query plan. So pretty standard kind of idea here. Kind of just to explain it a little bit more. So if you have a Sparkle query that says, for example, find messages where the creator's first name is John. So we have like 3 different triple patterns. This would be like the graph representation for the constants and variables in the query. So we would first turn this into a join graph. So each triple pattern becomes an element, a node in this join graph, and the shared variables, the join variables, are the edges between them. And then the query optimization processes, again, pretty standard, just finding an optimal join order. Each query plan has an associated cost, and the join order optimizer tries to find the plan with the least cost. Obviously, in this example, you would want to join the triple with the constant name. And of course, these kind of decisions are based on the statistics computed over the database. There are selectivity statistics to figure out which of these joins will be less costly. Okay, so, and again, the additional complexity is not just the join order, but what kind of join algorithms will be used. In certain cases, certain join orders will be preferable based on how the solutions are being generated in the child operators. Obviously, the source space is quite huge here. There are other factors such as like, again, in the pets query examples in the previous talk, like if there is a limit one in the query, you would want to use a streaming join algorithm because you are only trying to find the first answer. So those kind of things are taken into account. So what makes optimizations with LDBC, especially interactive complex workload, challenging? Well, the queries are quite complex, very large number of patterns in them. And as in one of the previous talks, there was, or maybe it wasn't here, but the point I'd like to make is, if you compare Sparkle to other graph query languages, some have more linear structure to it. So that linear structure in the graph query might give you a hint about execution order. Sparkle, more like SQL, doesn't have that linear structure. It has more nested structure in how you compose graph patterns together. So that results in a quite large source space for these join order optimization. And since cardinality estimations are very important to find the optimal join order, and in these complex query plans, small means estimations at the lower levels of the plan hierarchy can easily snowball at the larger parts of the graph. So we had to look into these kind of misestimations, for example, over the LDBC benchmark, and made some improvements. So it was certainly useful to make some improvements to our query engine on that front. As I mentioned at the very beginning, like, we didn't want to make any changes to the queries, but there were, for example, there are many examples where either variables are renamed, there are equality filters, or bind statements where a constant is assigned to a variable. So we have seen that in the context of really large queries, those kind of things were causing problems. And it would be easy to like rename the variables in the query and fix those, but we went ahead and made sure that our estimations and query planning work well. Then like 2 or 3 of these things are nested within a Sparkle query. And there are also other improvements we have done to the cardinality estimations. Cardinality estimations are challenging in general with relational databases as well, more so maybe with the graph systems, as the graph has a less regular structure. So we use some probabilistic data structures, which is typical to kind of track these cardinalities, the statistics about the graph, and use them to estimate the selectivity of patterns, joins, and so on. Finally, I'd like to mention one of the other challenges we have seen with, and this is a general problem, but we have seen this happening with LDBC benchmark, is also the non-determinism. Again, the complex queries might, the query planner, if it is starting to explore the search space using a different order, maybe after a restart or something like that, you can see the query performance change between for the same query, for the same data. So this is as challenging as making queries faster, making sure that the queries are reproducibly similar performance times at different times. And okay, to kind of conclude, some observations, maybe suggestions, discussion points for going forward for LDBC, maybe for consideration in the second version or later on. So one thing we notice is like access patterns are very similar in all of the IC query workload. Every query takes a person ID as an input parameter, which makes sense for most of the queries. But one thing that's very natural is looking up person by email, which is, an email is a multi-valued attribute. ID is like a primary key, but a person in the LDBC data model might have multiple emails. But I think still the email, I don't know exactly if the same email can be shared by multiple people, but this feels like a very natural query to write. These are the kind of queries we see in our like real world use cases. So I would suggest to kind of add different kind of access patterns to LDBC. Another suggestion I would have, like we talked that the schema flexibility as a differentiator for graph systems came up yesterday, for example, as the relational systems and graph systems was being compared. But LDBC right now has like a fixed schema, very fixed structure, which is obviously very useful in for a graph system to have a schema. But something that takes advantage of the schema changes on the fly, I think would be a very interesting addition to LDBC. And another point that we notice is like queries differ very widely based on implementations. Obviously, you can't compare like SQL queries with Cypher versus Sparkle in too much detail, but there are differences on even how like very simple things like date times are represented. Some systems might be representing them as just like epoch as in the queries. And I think my understanding right now is you can write the queries anywhere, any way you want at this point, as long as they get the same results. So an example subset from a query might have like 4 patterns and a filter, and I can just rewrite it to get rid of 2 of the patterns. It would return the exact same results. And my understanding is this is okay, and to some degree it makes sense to make like system specific changes. But my experience with other benchmarks is like the queries, the data model, you don't change because then that makes comparing different systems harder. So I don't know, this is kind of something that strikes me as different in LDBC and makes the comparisons across different systems a little more challenging. And yeah, that's all I had for today. If you have any questions, I'm happy to answer. And I might have said things that are not correct about LDBC, as I said, yeah, a little bit outsider. So if you have any corrections, I'm happy to hear that too.
All right, thanks. So Atanas posted a question in the chat about the scale factor of the benchmarks that you have shown on your slides.
We haven't gone larger than scale factor 10, so pretty small at this phase, mostly because, I mean, as I alluded to a little bit on the tooling challenges, but we plan to look at larger scales in the future. And what I was showing before, like it was the query mix per hour, I didn't explain it. It's not, we just create the query mix manually. Based on the parameters created by the data generator, but the queries were fixed.
Okay, Domagoj has his hand up.
Great, thanks. So you mentioned that you can return all paths, but when you talk about paths, you're always thinking about this finite length, no? That you bound from like 1 to 10, something like this.
Yeah, they are simple paths. So, but if you ask for all paths between 2 nodes, for example, it could return like paths of length 2 or 3 or 4. And obviously, this is typically not tractable. So typically, you would need to add like a max length restriction. There are some additional keywords that I didn't show, but
yeah. Okay. But so the system is gonna warn you this, right?
Warn, we don't really warn, but the query will take a long time and probably time out. The results are generated in a streaming fashion, so you would get like the shortest paths first, but after a while, it will time out or there will be another.
But so in theory, it's just gonna continue going, right?
Yes, in theory, it will continue going.
Okay, cool. Thanks.
Yeah, I mean, I think in our documentation, you say like this is not suggested on large graph sizes, all paths, but even shortest paths can be challenging. I mean, the all shortest path between two nodes.
Okay, question from Peter.
Hi. Thanks for the presentation. Nice. I was happy to see that you are using characteristic sets to combat the search space with star patterns. But my question is a different one, or actually my remark, because I think you rightfully say that in the interactive workload, the access patterns are quite similar.
Mm-hmm.
At least, they start as a single point, and then there are typically 2 steps of navigation from there. So that's that's the same across all queries. But I would like to recommend the BI workload now that we have kind of finishes, or there's a second workload on the same data set. And well, it will have very different access patterns, I promise.
Okay, yes, I mean, that's kind of in our to-do list. And yeah, we'll definitely check it out.
Cool.
Yeah, okay. If I may, yeah, first I'm very happy to see Stardog, following LDBC and using these benchmarks, and for quite a while, like including ourselves at Ontex, we've been citing from SMB, and now in the last 1 or 2 years we've been heading there. So we'll be very happy to cooperate, because I do believe that, well, although a typical RDF database is not optimized for this kind of loads, there is a lot of work to be done, and to be compared, and to see where the trade-offs are. So particularly on the we are currently just about to audit some benchmarks on SMB, but they are on a vanilla RDF version, and RDF star is obviously a better way for an RDF engine to deal with this. So yeah, we're happy to contribute and to share some experiences and to produce some standardized version of RDF star implementation of SMB that everyone can contribute to. So that's my quick note. And the last question is, you have your own Sparkle extensions that allow you to do pathfinding. Are those standard compliant, or you have to do some tweaks to the Sparkle syntax to get there?
I mean, if I go back to the example here, so what's the expressions you can put, like start and end nodes, or the links between them? These are like standard Sparkle expressions. You can put any Sparkle query here or here. So those are all standard Sparkle, but everything this is completely made up by us.
Okay, I mean, it's not rocket science. We did it. You can probably do it too if you want to. But there are standard compliant ways to get there, to let people a bit less confused.
And like
standard Sparkle or not.
Yeah, some systems, I think Peter mentioned, like Virtuoso had its own path finding extensions. And when you try to put the path finding into select queries in Sparkle, that's when it becomes a little unnatural. That's why we went with a complete new query form. separate from select, so that it would be more natural to return the path, all the nodes.
Yeah,
and,
okay, we can share some ideas of how this can be implemented without having to fork the Sparko parser. But that's not the big picture. The important thing for me is to make the message and to have the triple stores back in the game and really competing and having more than one. So that SMB and these kind of loads are no longer considered, the holy grail of property graphs. I don't believe they really are. It's just, over time we've been focusing on different things.
Yeah, happy to see more systems adopting the benchmark. Alistair had a question in the room.
I don't understand how it would be possible to introduce the concept of flexible schema into the benchmark, because either you have a situation where there is a schema that permits every possible insertion, and some data is not present, for example, in the generated data set, but it becomes present during the course of the execution of the benchmark. Well, that's fully compatible with a fixed schema. Or you would actually have to have some defined schema characteristics that would be required of the system under test, such that you would be able to illustrate, by virtue of actually having a schema that was enforced and a partials, and extensions beyond that schema that could potentially be permitted, in order to actually test this notion. It seems to me that we don't have the apparatus in terms of schema definition and partial schema definition to enable that to be evaluated.
I guess what I mean by schema changes could be as like there isn't any schema input in the social network benchmark, right? There's the data and there are the queries.
Yeah.
But you can imagine maybe a link from person to, a link between some of the two types here that's not in the initial generated data. Not necessarily a schema update operation, but having a relationship that wasn't fixed at the beginning. That's what I mean. And it's not very straightforward. I agree. It definitely needs a little thinking. But I think most people agree, it's certainly my opinion, that one of the big advantages of graph systems is that kind of flexibility. The use cases we see probably not very different than what you see, is like being able to connect disjoint data sources, being able to relate different schemas, and being able to do it without a big disruption to your current system. So a benchmark that kind of reflects that would be valuable is my point. But I don't have a easy solution about how to do it.
The fact that, the test has to be reproducible. So if you could insert data which expresses, for example, a relationship which is not expressed in the generated data, all that you've done is you've added another thing into this data model, and it's the point in time at which the data is being generated is different, but it doesn't mean that so I could take an SQL database, provide a schema, have some part of that schema not be populated at all in terms of the actual instance, and then later on during the course of the test it becomes populated. I don't think that really illustrates schema flexibility. It's a different step.
Yeah, I'm just thinking out loud now, but looking at this model, for example.
Well, I'm just, I thought it was an interesting comment.
Just to illustrate what I'm talking about, like you can think of like companies linked to country directly, but person is always linked from city to country. You can think of an update coming that links a person to country directly. And you might have queries that's looking at who's located in the country without limiting it to companies initially. So as the updates come, the results will return not just companies, but per people as well.
Okay, well, let's follow up with your suggestion through email. That would be ideal to discuss.
Yeah,
Yeah.
I just want to say that that's an interesting discussion for us too. I appreciate that benchmarking under such circumstances would be quite a challenge. setting yeah, what you expect to get out of it, but that's really part of the added value of these systems.